So here we go. Now, which one did you have a question on? Is that one?
27.
That's the one. And so, go ahead and read 27 for us.
A particle revolves in a horizontal circle of radius 2.90 meters. At a particular instant, its acceleration is 1.05 meters per second squared, in a direction that makes an angle of 32 degrees to its direction of motion. Determine its speed, A, in parentheses, at this moment, and B, 2.00 seconds later, assuming constant tangential acceleration.
So the acceleration is 1.50 meters per second squared?
1.05.
1.05. And it makes an angle of how much?
32 degrees.
It makes an angle of 32 degrees with its velocity. Here. Okay. So there, yes, there was no trig that was needed beyond your simple sines and cosines. We have a velocity here, and the key point is that my acceleration vector can be thought of in terms of two components. One is tangential to the circle, and it will be in the same direction or opposite direction as the velocity. And so I can immediately draw a component of my acceleration right here, like this, and a second component perpendicular to it right here, like this. And this guy is the centripetal, and this guy is the tangential component. And so the key to visualizing it is the tangential component is going to be parallel to the velocity tangent to the circle there. And so since we're given a 32-degree angle, and we have a nice little right triangle, with a 32-degree angle right there, and I'm betting that if I turn you loose, you can finish the spot, right? Yep. So I'll let you do that. You know the angle.
Yeah.
You know the hypotenuse.
Okay, yeah. Okay.
Yep. Okay, now number 26 you said, right? A car at Indianapolis 500 accelerates uniformly, going from rest to very fast. In a semicircular arc with a radius south, determine what's happening to the turn, blah, blah, blah. Okay, tell me what you did with it. This is a good problem because what it requires you to do is to coordinate a large amount of information, but it's not a hard problem because it's going to simply rely on the equations of motion that you know and love and so on and so forth. So Tiffany, this is your question. Tell us what you think.
Well, yeah. Okay. First I have a halfway point. It's like I'm halfway around
So we'll have them start here. How about we start them from here? And we'll go together.
And so I did the circumference, which is 2 pi times 220 meters, and then I divided it by 2, which comes out to 691.
695?
91.
691 meters. Okay.
And so to find the tangential acceleration, I used the v squared equals v squared plus 2a delta x.
Good.
And so I plugged in 89 for v.
Is that how fast he's going at the end of all that?
Yeah.
And 89 what?
Meters per second squared. Yeah.
How did you know it was 89 meters per second?
Converted it. Oh yeah.
Converted it.
20
Okay, good.
And then 0 is the VO. Starts to fast. And then 691 is delta x.
Good, good. Okay.
You do that a lot faster than I did.
That's going to give 810 divided by 2 divided by 691. So your acceleration turns out to be less than 1 meter per second squared. Is that right?
I got 5.7.
7, not 2.
Oh, yeah, you're right. 4.17?
5.7.
5.7. Okay. So far, you are doing great notice that she's doing something that's very sophisticated, and yet it's exactly correct. She's treating this circular arc motion as if it were a straight line. In other words, she's having the car go around like this. She's just sort of unbending the circle to treat it as if it were linear motion, hence equations of motion for acceleration in a straight line. And that makes total sense. All right, keep going.
And then so to find the time when it's going, like maybe to find the time when it's like at the halfway mark, I use V equals VO plus KT.
Okay. Tell me what you're planning to do at this time before we get into that calculation.
To find the time so that, because I'm pretty sure the velocities aren't they in the tangential direction, so you can't seem to find the centrifugal force, or not centrifugal force, acceleration.
And that's what made the problem difficult, was that assumption right there. Actually, you are going to use exactly this speed,
Okay.
which is the magnitude of the velocity vector. The velocity vector is always tangent to the circle, and it is its magnitude, which is the speed of the car, that determines the amount of centripetal acceleration needed to pull that thing in circular motion. So now that you know that, how would you find the centripetal acceleration?
Oh, you just use V squared over R.
That's it. That's it. And that gives us 89 squared, again, divided by the radius of 220. And let's see if I can do this a little better this time. So 90 times 90 ought to be 8100 divided by 220 ought to be about a little under 40, about 37 meters per second squared. Is that right?
Wait, I got 62.
I got the velocity, I got 62.8 because it said halfway around the
That's
circle.
62.9.
So it wasn't fully at the end.
Interesting. Interesting. So if we rest to 320, a semicircular arc, radius of.
I found it differently.
Well, I approve of all the calculations she did. You got the final velocity of 62?
Because
It's half.
it was at halfway, so it wasn't at the full velocity yet. Because it said
Define the tangential and radial acceleration when it is halfway through the circle.
Oh, I see. I misread it. I thought the turn was the full way around, and so semicircular took us. Aha! Aha, aha, aha. Okay, T-Fame, do you agree that we misread the problem together?
Yeah, I think, well, I didn't do it like that.
Okay.
And I just did I tried to find the time, but I think I did better now.
Yeah. This would give us, if we actually completed this, this would give us the correct answers to the wrong question. T-Fame and I together found the components of acceleration at the end of the semicircular turn, which is not the same as halfway through the semicircular turn.
Wait, what did you find?
Yeah.
I'm confused.
Yeah? There we go. At 36 meters per second squared. All right, so the question is worded in kind of a tricky way. The car is going through a semicircular turn, right? But then if you look closely, the question asks you to find the components of acceleration when it is halfway through the turn.
so it's half
So
the half.
So it's half of the half, that's right. The turn itself is a semicircle, and it wants
I
to
really should have
know.
asked a question when we wrote about this, because it's a long time.
It took me a correct.
I solved it, but I used the wrong radius. So.
And there you go. Okay,
We could have
So-
another discussion.
so to do this right, see, why don't you put these things on in there?
I will.
Why?
I always feel like I'm the
I thought
only one. I always feel like I'm the only
So
one.
what? So what? Is he the only one that has trouble with these questions? No. Come on, people, be a community, not lone rangers. Be a community. All right. So what do we need to do, given that all this is incorrect? Of course, we're not just going to scrap and start over. tell us what we need to do to go through and fix it. What has to change here? Yeah,
Okay, so you got the 5.72, right?
yeah.
So I did, b squared is equal to,
Yeah.
well, I did b is equal to the square root of b o squared plus 2a,
Okay.
and then times delta x,
Yep, so what changes here?
the bottom.
The bottom.
No,
Yeah.
like,
This is all good?
that whole, yeah,
That's all good.
That's all.
yeah, and then that stuff.
So I use the same equation to find the velocity, but I just plugged in the tangential acceleration.
Gotcha. Okay. That's what she's saying. I'm a little slow this morning.
It's a lot slower.
We're gonna fix this. She solved for, and so we're gonna have 0 plus 2 times the acceleration that she found times our delta x, and our delta x is going to be half of this, right?
Yes, after this one.
Yeah.
So that's going to
I
be,
just scrapped the 2.
yeah, exactly, 691 over 2, and cancel. And so that's going to give me about 5.5 times 700, about square root of, it's about 40, something like that. You said it was 60?
17. Oh yeah, the 62.8.
62 meters per second is the velocity right here.
Yeah. And then
Good. Okay. And so now, Tife, where are we going to go from here?
B squared over I.
And so that gives us now 62.8 meters per second squared divided by a radius of 220, which comes out to 18.
you rounded up.
Yeah. I use 62.
That'll do. So we notice an interesting thing as we go back and we fix this, and that is that our tangential acceleration didn't change. That calculation was good. It was simply that the centripetal acceleration will change, will it go up or down as the car goes? It's going to go up because the speed of the car is going to increase.
It also says assuming constant tangential acceleration, so that's
Yes.
good.
Yep. Better? Okay, good. Well, let's get to today's lesson, which is interesting and has a lot of interesting history involved with it. Today we're going to talk about the general or universal law of gravitation, which is attributed to Newton, but he gets more credit than he deserves. It really should be a shared credit situation. Okay. We're going to take a walk through history of our understanding of planets and their motion. Who can tell me why planets are called planets? Anybody know? If you were to just look out in the sky, you would think that planets are what? Stars. That's exactly right. But there's something funny about them.
They have gravity.
They do, so do stars. But there's something funny about them if you're observing. If you're, who was famous for doing observations of stars? Galileo. Back up. Before Galileo. Kepler. Ptolemy. Very good, very good. Those are all going to be players in our story. Back up even further. Ptolemy is about 100 AD, 150 AD. So go back to BC times. Egypt? Yes. And the Babylonians even more so. And the reason that we care about the Babylonians is actually because the Babylonians are responsible for a strange historical accident. The Babylonians believed that the number 6 was magical. And so everything they did was in sixes. And as they observed the stars, they would set up large circles of stones. And these large circles of stones would be divided into groups of 6, or 6 times 6. Hence, 360 degrees in a circle. We get that from the Babylonians. There's no particular reason that it ought to be 360. It'd be a lot more convenient if it was 100, right? But it's 360 because the Babylonians believed that 6 was magical. That's it. All right. So, when people tell me that degrees are friendlier than radians, I just tell them, not really. Degrees are really arbitrary. Well, as a result of observations of the stars, the Babylonians and others discovered that certain stars don't behave properly. Throughout the year, it should be the case that these stars should take a nice circular course of some sort or another. But it turns out that certain stars would actually take a course that goes like this, and then backwards a little bit, and then forwards a little bit, and then backwards a little bit, and forwards a little bit. So these were called the wanderers, which in Greek is planets. So the planets are called planets because they, quote, wander across the heavens instead of going in a nice, regular angular pattern. So the next question is, why do they do that? And so the first person to tackle this in a systematic way was Ptolemy. And I forget the name of his book. I was looking at it last night. But around 150 AD, he produces a work in which he plots out the known trajectories of all of the stars that he could see. There's about 1,100 stars. Why would you want to do such a thing? Okay, but think more practically. These people aren't just doing it for their health. Well, they are.
Navigation.
What's that?
Navigation.
Navigation is one thing. Yes. What else?
I was gonna say like time instead of being like until the seasons change or like policy.
Bingo! Exactly. Agricultural. Ptolemy's primary interest is going to be agricultural and then astrological also, because there's a belief that the stars are going to control your destiny, and that belief actually persists all the way up into the 16th century. And well, I guess until today, if you have people that read their horoscopes. Have you ever thought it really strange that everybody born in 1 month all has the same horoscope?
Well, it's not exactly 1 month. It's like kind of 1 month, and then the start of another.
But it's a 1/12 of a year period.
Yeah.
Yeah.
What? So it's 2 months.
There's no idea.
He's a big, yeah.
By the way, the word month is related to what other common English word?
This is cool. No, it's not. You don't use a silent letter for your English. It's not. I'm trying to learn something.
The word month is related to what other common English word?
Long.
What did you know?
Stupid law.
Yeah.
Roughly the period of time that what goes in a full cycle. A moon. That's it. That's right. A month is really a moon. It's really roughly the period of time. Now it turns out that lunar months, there are actually 13 lunar months-ish in a year, right? But they got regularized, well, really because of the Romans. Anyway, he has tracks for 1,100 stars, and he also has a model which is called a geocentric model. In his model, the Earth is at the center. In other words, it is geocentric.
What did they think about the sun?
What did he think about it?
Like-
What did Ptolemy think about it?
Yeah.
Well, what do you see when you watch the sun over the course of a day? What does it do?
Here.
See, it
So
goes
you
back
think
here.
it goes so they thought it went around the earth.
He believed that the sun went around the earth, and he had, I wish I could pull it out for you. I should do that. I should put that out there so you can see it. but the moon was on the inside, the sun was after that, the planets were after that, and the fixed stars were out further than that. But the question is, how do I account for the planets? And the way that Ptolemy did it is that he has all of the objects in cycles, in other words, periodic rotations, and he has the planets with epicycles, cycles upon cycles. So if this is the Earth here, then our first track out is going to be the moon. And we're going to have the sun, drawing not to scale. And then we're going to have planets. And so my planet takes a cycle around the Earth. And at the same time, it is doing a little epicycle around its own cycle. And that accounts for the back and forth motion. See? Ta-da. Here's the wild thing about this. Ptolemy's work, which is a legitimate scientific work, it's accounting for the observations that we see, lasts up through the 17th century. That's not a bad track record, considering. It works really, really well. In particular, it worked really, really well for the planting of crops. So this was a practical, useful, and in some ways correct view of the universe, in that it accounts for the observations that we see. Or at least it accounts for the motion of the stars that we see. His was not the only one. Aristarchus, who lived actually BC, believed that the sun was at the center of the universe. How about that? And so there were a small number of people that were what we call heliocentric. Well, this idea, however, lays mostly dormant until our next player, who is Copernicus. And Copernicus is going to publish in 1543 a heliocentric model. And in the heliocentric model, the sun is at the center of the universe, and the inner planets, Venus and Mercury, are going to go around the sun, and then the Earth is going to go around the sun, and then the other planets out here are going to go around the sun, and then the fixed stars are way out there, and they're going around the sun as well. So why would Copernicus want to do this? What would make him suspect that this happens? Well, Copernicus realized, he was able to sort of visualize it, he realized that if you do this, then all the epicycles go away. So it really becomes a simpler way of thinking about it. The issue is not, is it more correct, but is it simpler to think about it in this way? And the answer turned out to be yes. So it simplifies by removing epicycles. But it does something else too, and that is that it accounted for an observation that I think Ptolemy really didn't either notice or have an answer for, and that is that it accounted for the fact that the planets appear to get brighter or dimmer based upon the time of year. Well, why would that happen? In Ptolemy's system, it doesn't make a whole lot of sense, because the epicycles aren't that big anyway, right? So in Ptolemy's system, the planets should be basically all the same brightness all the time. But for Copernicus now, this makes a whole lot of sense. If Venus is back over here, well, if Venus is back over here, we're not going to see it because the sun's going to be in the way. But let's take Mars or something like that. So here's Mars right here. And if Mars is in opposition so that it's all the way down over here, it's going to be a lot dimmer. And if it's up here, it's going to be a whole lot brighter. So Copernicus' system, not only it simplifies, which is great, but it also accounts for new data. It allows us it explains the varying brightness of the planets, which is something that the fixed stars don't actually do. They don't get dimmer and brighter. Well, the variable stars do, but that's a whole other story. That's because they're actually twins. Copernicus's ideas didn't catch on a whole lot, but they also were not amazingly controversial. There were only a few people who basically championed the heliocentric theory, but it was spread really without comment until 1610, in which Galileo began to vocally defend the heliocentric theory. And the issue here gets complicated because you have multiple players. Galileo builds a telescope, and with his telescope he is able to observe some things. First of all, he observes shadows on the moon in the moon's what we now know to be craters, and he infers that there are mountains and craters on the moon. And the second thing is that he observes that Jupiter has moons. Now, why is this a problem? Well, the top was a real problem because if the moon has shadows and craters, then it actually has depth to it. And the difficulty with that is that it called into serious question Aristotle's understanding of how motion worked. In Aristotle, you remember that we encountered Aristotle before. He believed that heavier objects fall faster, right? Well, he also believed that all objects had a natural tendency to fall towards the Earth. And since the moon is self-evidently not crashing into the Earth, it therefore follows that the moon is not an object with mass. It has to be just a flat disk painted upon the cycle that Ptolemy had laid out. So the moon has depth, means that the moon has mass, which means that the moon is an object with mass that is not falling to the Earth, and Aristotle is wrong about his understanding of motion. Well, Europe at that time was a hotbed of exploration of motion and other ideas. And the church was intertwined with universities at that time. Theology was considered the queen of the sciences. It was organizing all information under the rubric of this is how God made it, was considered to be the height of knowledge. And in particular, it was understood that all knowledge that we had acquired had to be consistent with Catholic doctrine. And so now a food fight starts with Jesuits. And the food fight results in Galileo being under house arrest and under suspicion of heresy. In particular, the heresy that he was supposed to have promulgated was the idea that the Earth goes around the Sun, and the Sun does not go around the Earth. And this was considered heretical, really because it ran counter to this whole line of theological thinking that was actually indebted to Aristotle and not the Bible at all. And we understand now that when the Bible talks about the sun going through its courses in the heavens, it's speaking in terms of what we see. What we see is the sun going through its courses in the heavens, and that's what the Hebrews were talking about. They weren't trying to provide a technical scientific explanation for what's going on here. So as a result, heliocentrism ended up with a kind of a bad name in some ways. However, we now have two other players that come onto the scene with a lot of observation. One of them was a very interesting man named Tycho Brahe. He actually precedes Galileo just a little bit. Brahe. By the way, these are not the dates in which they were born. These are the dates in which they are actually publishing their stuff.
That would be impressive.
Yeah, no. Notice that we've got a long period of time going on here. He was a really interesting guy. He had a metal false nose that was made out of brass. He had a pet elk that died by getting drunk at a party. And he also had several different observatories. And one of them was essentially a learning institute that had about 100 different apprentices at it. And one of them was our friend Johannes Kepler. And Brahe compiled, during this time period, he compiled large amounts of observations about the heavens. And his student and assistant was Kepler, who in 1611 publishes a very important work called the Somnium, in which he describes a dream in which his mother goes to the moon and sees the entire universe as viewed from the moon instead of from the earth. Notice what he's doing. He's rethinking his reference. Right? He's placing his origin at a different point and asking, what does this look like? Have you ever tried to do that before? Have you ever tried to imagine what something looks like from a different location? Like,
Yeah, like around.
like a mountain. Sort of picture it. That's exactly what he's doing here. And he publishes a second work in 1618 called the Harmonices Mundi, which is yes, all scientific works at this time were published in Latin because that would allow you to communicate with the whole world, which did not necessarily speak Italian or Danish or German or whatever. And in the Harmonices Mundi, Kepler publishes a heliocentric, I'm wrong, a heliocentric picture, but he also proposes 3 laws of motion of planets that we will actually discuss this week, but not today. And his laws of motion the story goes, he was able to figure them out by taking beer barrels and sort of arranging them so that he could get his point of view, his reference frame figured out. But importantly, one of the laws of motion that he discovers is that the period of rotation of these planets is proportional to the distance to the 3/2 power, which is kind of wild.
The distance from the Earth?
From the sun. From the sun. Or in the case of the moon, which is going around the Earth, the distance from the moon. In other words, the period of each satellite is going to be proportional to the 3/2 power of its distance. And this opens now the possibility of doing some mathematical analysis. And that mathematical analysis is taken up by several people. One of them is Hooke. One of them is Christopher Wren, the architect who built Shakespeare's theater. And he built several other things. And one of them is Sir Isaac Newton. And in 1687, he publishes the Principia, which is the work which gives us calculus, at least in England, Leibniz is going to contest that on the continent with his own works. And he proposes the universal law of gravity that we're going to study today. True to form, when Newton publishes this, he begins now a priority dispute with these guys about who discovered the universal law of gravity first. It's universally recognized now that all of these guys deserve some credit for it. Hooke was the first person to sort of suggest it. Newton was the first person to really prove it with detailed observations. But even there, his observations were not perfect.
What did Christopher Wren?
He actually had a discussion with Newton in which these things were hashed out. Yeah. Even there, the universal law of gravity was not perfect because the moon wasn't behaving exactly as it ought to be. It was not until Leonard Euler comes along, almost a century later, and Laplace, and factored in the effects that the other planets have on the moon, that those small little details were straightened out. All right. So, what is Newton's universal law of gravity? Without further ado, here's the form. What Newton discovered is that the gravitational force is proportional to, or is a constant times, the product of the two masses being attracted divided by the square of their distance.
Can you repeat
Yep. Right there.
that?
So the product of the two masses divided by the square of their distance. In other words, if I have the Earth and if I have the Moon, then the center to center distance, please note it's not the surface to center distance, but the center to center distance between the two is going to be the radius r, and the mass of the Earth and the mass of the Moon are now the masses that go into our planet world here. Now, interestingly, yes,
Sorry.
that's fine.
G is gravity which
So G is a constant, and it's called the universal gravitational constant. And it's true not just, its value, is constant, not just near the Earth, but also in the solar system. And now we know for all stars ever. Here's the interesting thing, though. Well, let me point out some things about this, and then I'll take it from there. First thing that I want you to observe about this law is that it is symmetric. Because I can exchange the M2 and the M1, and I don't change the value of the force. And what this means is that the amount of gravitational force that the Earth exerts on, say, me, is equal, but opposite to, the amount of gravitational force that I exert on the Earth. Just as much force, but as we discussed before, not just as much acceleration, because of the different masses. So it's symmetric, and that's really Newton's third law. Second thing that I want you to observe is that because the r squared here is in the denominator, larger values of r give you weaker values of gravitational force. The further you get away from the Earth, the weaker gravity becomes. So we call this an inverse square law, because the force drops off with the square of the radius. That means that if I go twice as far away, my force is going to be 1/4 of the value that it was. If I go to a distance of 3r, my gravitational force will only be 1/9 of the distance of the force at distance r. Yes.
So for every G, do you get value from there?
Yes, I'm coming to that. Interestingly, Newton knew The acceleration due to gravity near Earth, what is that value? 9.80. But he did not know the value of the universal gravitational constant because he didn't know how heavy the Earth was. He needed to know the mass of the Earth in order to figure out the value of g, or vice versa. This value was not actually known for another 117 years. Until Cavendish comes along, and he is the last person in our story. And I think I'll tell the whole story tomorrow, because I'll run out of time if I try to tell it right now. Cavendish runs an experiment that we call weighing the Earth. And I will save you the details for tomorrow, except to say that Cavendish discovers that the value of g is 6.67 times 10 to the negative 11th. And now we have units that in our time would be written as Newton meters squared per kilogram squared. But those units should not intimidate you. All they're doing is canceling out the other units in the formula to give you newtons. And once this value was known, we could now reverse engineer and go back and figure out the mass of the Earth, which he did immediately, to discover that the mass of the Earth is 5.98 times 10 to the 24th kilograms. It's the heaviest object in the world. The sun's even bigger, 10 to the 31st kilograms. It's just too much. That's right. That's exactly right. Now, I had some goals for you guys to be able to do some things, and we'll see if we can get this. But the thing that I want you to see is that there is going to be a big
Oh,
objection
that's
to
a
this.
4. I thought that was 211.
No, 10 to the 24th kilograms.
Okay.
I thought the equation was m comma mz before the page before.
Okay.
I figured it out.
Okay, yeah, so let's be clear here. The force due to gravity anywhere in the universe is going to be this constant g, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times the product of the masses of the attracting objects divided by the square of the distance. Okay. Just too much to say, so I'll say some of it tomorrow. There's going to be a complaint, and the complaint about Newton's law is that it appears to involve action at a distance. Think about it. Star Wars aside, can I do this and move you? No, why not? Because I'm not touching you, right? I can't actually exert a force on you unless I'm touching you. How is it that two objects can exert a gravitational force on each other at a distance? Leibniz is going to complain loudly about this problem. He does not like it. He is going to argue that there has to be some kind of, quote, gravitational vortex, an idea that he gets from Descartes, that is going to somehow ripple outwards and suck things in. That idea is actually going to be the genesis of Einstein's notion of relativity. I want to tell that story tomorrow. Here's the thing you need to be able to do today. Two things. Number one, you need to be able to compute the force between two objects, and that's easy. The force of gravity is just the formula, gm over r squared. And likewise, you need to be able to compute the gravitational pull for a field or attraction for the gravitational acceleration that an object is going to have around it, such as the Earth. And that's computed by taking force and dividing it by mass. Because if I have a large object here, say the moon, and I have a small object, say me, floating around the moon, then my force is going to be singular. It's going to have a single force pulling straight down. And since it's a gravitational force, I would label that as mg, right? But also, now with my newfound formula, I would also label that as g times the mass of the moon times the mass of me over r squared. And if we just cancel out my mass, and we're kind of used to canceling out masses, then we see that the gravitational field generated around an object is going to be g times the mass of that object divided by the square of the distance that we are talking about. So if I knew, and I do, know the mass and the radius of the Earth, I should be able to calculate the acceleration due to gravity. Let's see. See if it works. For the Earth, we have g times the mass of the Earth divided by the radius of the Earth squared. And looking up those numbers on Google or in the back of the book, we get 6.67 times 10 to the minus 11. That's 5.98 times 10 to the 24th kilograms. Divided by the square of the radius of the Earth. Radius of the Earth is 6 times 10 to the 6th meters, but I need a more precise thing here. Earth, radius 6.38 times 10 to the 6th meters squared. And when you actually punch the numbers in, then lo and behold, you're going to get something very close to 9.8. It comes out to 9.80. Yep. Okay. With all that in mind, I'll see you tomorrow.